Now we'll discuss oxidation reactions of alcohols. Primary and secondary alcohols can be oxidized using oxidizing agents such as sodium dichromate in a Jones oxidation. In one of these oxidations, a primary alcohol will be converted all the way to a carboxylic acid. Basically, we will remove these two protons, add an additional oxygen atom, and then oxidize it. A secondary alcohol, because it only has a single proton here, will only be oxidized once to generate the ketone. How does this reaction work? First, an alcohol will react with chromic acid, which is generated naturally when we add sodium dichromate in a sulfuric acid solution. This acid will interconvert between the alcohol form and this chromate ester. The chromate ester, in the presence of water, can be deprotonated here, which would form a new double bond between the carbon and the oxygen, and kick off this chromium breaking one of these bonds. This generates our aldehyde, in this case, as well as this negatively charged species, which is stabilized by resonance. Next, our aldehyde will interconvert in an aqueous solution to this hydrate form, where we've got another alcohol. This alcohol can then be resubjected to another equivalent of the chromic acid. The reaction will repeat, and we will generate a new double bond and our carboxylic acid product. Again, because a secondary alcohol only has one hydrogen, this reaction will only proceed once. There are some cases where we want to convert a primary alcohol to an aldehyde instead of converting it all the way to a carboxylic acid. Whenever we do a Jones oxidation, the carboxylic acid form will always be favored. We will not be able to stop at the aldehyde stage. The reagent we use in this case is pyridinium chlorochromate, or PCC. If we take a primary alcohol under Jones oxidation conditions, we make a carboxylic acid. If we use PCC instead, we can stop at this aldehyde stage. The structure of PCC is actually what lends to the reactivity that we see. It's pyridinium, so we have a pyridine which is protonated, that's why it's pyridinium, and this chlorochromate group. This is actually soluble in organic solvent, which means there's no water present in this reaction. That's going to be important later. Just as in a Jones oxidation, our alcohol and the chlorochromate in this case will act in an equilibrium reaction to generate our chromate ester. Now the chloride, instead of water in this case, because there is no water, will act as a base, deprotonate here, form our new double bond, and generate that same negatively charged species we saw before. However, this reaction in a Jones oxidation would continue by forming a hydrate because of the water present. In the case of PCC, because we're using organic solvent with no water present, this reaction is eliminated, which means we can't form the hydrate and we can't perform a second oxidation to generate the carboxylic acid. So in this case, the lack of water will result in the formation of only the aldehyde product. To summarize, primary alcohols can be oxidized all the way to carboxylic acids using a Jones oxidation. If we want to stop at an aldehyde, we would use a PCC oxidation. Either one of these two conditions can be used to oxidize a secondary alcohol to a ketone. However, a tertiary alcohol just can't be oxidized because there's no hydrogen that can be eliminated to form our new double bond.